and future work. Good afternoon, everybody. Today I'm going to present the work titled Derivative-Free Self-Optimizing Control with Stochastic Multi-Start, Convergence Analysis and Benchmark Example, developed by me, Jairo, under supervision of Dr. YangQuan and with cooperation of Justus and from University of California, Merced, and with the support of Mingzheng and Chuang from Hainan University. The outline for today includes an introduction regarding self-optimizing control, the theoretical convergence analysis for SOC, a case study for numerical simulation to validate the theoretical convergence results, and conclusions and future work. The self-optimizing control can be divided in four categories: the perturbant observed type controllers, like extremum seeking or maximum power point tracking; the traditional self-optimizing control proposed by Stochastic for systems with thousands or hundreds of control variables, where a cost function is introduced to select the best control variables at each moment. Some batch-style controls like run-to-run and iterative learning control, or the ones that we're interested today that are the real-time optimization that includes zero-order or derivative-free algorithms or gradient-based optimization methods. In this paper, the self-optimizing control scheme proposed is shown on the figure. As you can see here, it consists of a closed-loop stable system, which in this case is represented for a first-order plus deadline system and is represented for a PI controller, which on top of that, a supervisory layer is added, which contains a real-time optimization algorithm or self-optimizing controller, which in this case will take the reference error and output signal to minimize a cost function, which is in base of the time domain desired specs of the system. You overshoot setting time and integral of a square error. In this case, the parameters of the controller Kp and Ki will be optimized based on a batch-to-batch execution given by a periodic reference signal in order to improve the performance of the system to keep the desired overshoot and setting time, as well as subject these constraints in terms of the proportional and integral gain. Likewise, the optimization algorithm used in this system is the globalized constraint Nelder-Mead optimization. This globalized constraint Nelder-Mead basically employs a real-time execution of the Nelder-Mead, which is executed in a batch-to-batch scheme, where the Nelder-Mead derivative-free optimization method is executed. And there are two features added in this sense. One is that we have a local search stage, where is the Nelder-Mead, and we have a probabilistic restart. Once the Nelder-Mead convergence is reached, we evaluate if the solution satisfies the conditions. Otherwise, we restart the search of the classical of the Nelder-Mead on a different initial condition. So in that sense, we have a probabilistic restart, so we can reach the global optimal solution for the proposed. In order to prove the convergence and stability of the GCNM algorithm, the following considerations must be considered. The first one is that GCNM is a derivative-free algorithm. Therefore, classical tools like Lyapunov contraction map are not applicable. In the same way, as the multi-star approach is employed, the randomness and stochastic behavior is introduced into the algorithm. And in the same way, the stability needs to be considered for the closed loop control that is optimized at each batch time. Therefore, how we can perform this theoretical analysis will be the question for this presentation. In order to analyze the GCNM convergence, the algorithm is divided into stages. The first stage is the global stage composed by the random search, and we have a local stage that is composed by the Nelder-Mead. The first stage corresponding to the random search can be analyzed using some of the existing results on random search convergence and probability problem. So the pure random search can be defined as this cost function, where based on the probability, the algorithm will converge into the desired solution as the execution or the iterations goes to infinity. In order to achieve that, therefore, In order to achieve the convergence, we can use the theorem for convergence proposed by Merced, which basically makes sure that if we are in a constrained domain D for the solutions, that is the search space for the randomness, and the probability limit is bounded between plus minus infinity, and we suppose that the cost function has with probability 1 optimal value, so we can tell that as the iteration axis or the time axis goes to infinity, the probability distribution of the solutions will lead us into the global convergence or global solution. In the same way, when we go to the local stage, that is the Neldermeet, it's important to notice that we need to use some methodology that let us analyze the shape of the Neldermeet in the n-dimensional space that we have. In that way, we can use the frame-based methodology proposed by Bayat, which basically assumes that the simplex of the Neldermeet can be defined as a frame, and we can measure or be aware of the deformation of that simplex in the sense that we can determine whether our simplex will be shrinking so much so it loses shape and the convergence is done. So this frame-based theory is based on the definition of frame, and this frame basically is formed by several positive bases, as we can see here. And the base idea is that these bases should satisfy these magnitude conditions and these norm conditions in order to make sure that our base is not vanishing as we perform the optimization. In that sense, this is the positive base, which is the points of the simplex plus the average of those points. And if we define some boundaries for the magnitude of this base, in that sense, we can define something called a minimal frame or quasi-minimal frame, which is basically the minimum size of that shape of the simplex that will continue satisfying the performance for a good optimization. So this frame-based algorithm is based on two conditions, that is the inner loop condition and the outer loop condition. Based on these two, basically the inner loop condition is the execution of the Neldermeet by itself, and we can in that sense make sure that if we are accounting for that deformation of the simplex, our self-optimizing controller, in this case our Neldermeet, will be achieving an optimal point. So using theorem 2 proposed by Bayat, we can tell that if the sequence of points that we are evaluating are bounded, and if our function is continuously differentiable and is bounded into a region R, and we satisfy that the conditions for the magnitude and the determinant of the positive frame base is satisfied, we can tell that as k go to infinity, our Neldermeet or our base will converge into the optimal value. That will be the function of this theorem. In that sense, if we want to use that idea for our Neldermeet problem, we need to modify a little bit the globalized constraint Neldermeet in order to make it fit with these two definitions: the global search produced by the random for the pure random searching, and the modified Neldermeet to account for the simplex deformation and be able to use the tools described before. So in that sense, the modified Neldermeet basically will account for the simplex deformation based on the proposed limits and in this stopping condition and scaling factor. In that sense, we can redefine our globalized constraint Neldermeet, as we can see here, extending the points of the Neldermeet by 1 if we are in a two-dimensional search like the PI controller. And based on that definition, we can prove the stability of the convergence of the Neldermeet. So we need to do one additional assumption, that in this case is that the optimization parameters should be constrained into a domain that is that makes the closed loop system stable, and that our optimization always operate on within that range, ensuring that we are not having unstable poles on our system. In that sense, we will have this structure to analyze the SOC convergence. So let's analyze first the global stage. In this case, applying theorem 1, we can set that the probability distribution is given by a normal distribution, and we are bounded between a safety set. And our cost function is smooth and stable and has a value, a global optimal value. And based on the assumption 1, and our system is not empty, so the distribution, we can ensure that the random search will be optimal and reach the global solution as the time or the iteration axis goes to infinity. In the same sense, we can do the same with the globalized constraint Elder-Mead. We can satisfy the 4 conditions for the theorem. The sequence of the frame increases. We satisfy the stability assumption conditions. We monitor the deformation of the simplex using the magnitude and the determinant of the simplex, and in this case, every time our frame is a non-minimum frame, so we can readjust if the simplex is deviating. So based on that, we can tell that based on both analysis, both global and local, the self-optimizing controller bounded into that domain will be able to converge into the global optimal solution as k go to infinity, assuming and satisfying the condition D and satisfying theorem 1 to 2. In order to validate this, we use the numerical analysis. In here, we make some test bench for the system for different time delays, 0.1, 1, and 10, and for some specific desired overshoot and settling time conditions using different performance indices. As you can see here as example, the globalized constraint Elder-Mead is able to converge into the desired condition in around 40 iterations. And the same result repeats for 1 and repeats for 10. This is 30 runs for each of the, 30 runs. So our controller is able to converge in a reasonable time. This is the global analytics. As you can see here, for the convergence times, the overshoot, we are satisfying the initial conditions for both things, for both specifications. In that sense, we can tell that we can analyze the convergence of the self-optimizing control framework presented on this work using the pure random search-based theory and the modified Elder-Mead optimization algorithm for the local stage. The frame method allows us to have a framework where we can use and be aware of the simplex deformation to monitor and improve the controller performance and ensure the global optimality. In that sense, this methodology based on the global and local algorithm can be extended to replacing the Elder-Mead for other optimization strategies like SPSA, simultaneous perturbation, stochastic approximation, or other gradient-based methodologies where we can use both global and local strategies to ensure the convergence of these strategies. Some reference.
Thanks for your attention.